Hey, good morning. Welcome to the class. So let's wait for a few seconds and then we will start today's topic. Again, if you have any questions, please, don't hesitate and type it on the discussion board so that I can address you during the break. Okay. Okay, so let's start the class. So today, let's see if we can finish two related topic in one shot. Okay. So the first thing that I want to talk about is something called the minimum spanning tree problem. So we will talk about what is this problem and then talk about some history about this problem. And then we will introduce three different algorithms for solving it. So these algorithms are based on some different strategy. Okay. So first of all, what is the minimum spanning tree? We have an input graph G. So let's say, first of all, before we mention this minimum spanning tree problem, let's talk about a related problem. So given a graph G, which is undirected and also connected, a spanning tree of the graph is a tree such that it connects all the vertices together. So imagine, if you consider all the edges, the red edges and the blue edges, then this is the original graph. But what we want to find here is we want to connect the vertices together by some tree structure. So if you look at the blue edges, by using only the blue edges, then we will see that the resulting graph using the blue edges is now connected. And then we call this subgraph with the blue edges a spanning tree. Okay. Now notice that we just need a tree to connect all the vertices together. It is because if it is, so what is a tree? A tree is a connected graph without any cycle, right? So this is a definition. So if there is a certain cycle inside the graph, let's say we have an additional edge here together. So the graph is still connected, but then we will see that because there is a certain cycle in the graph, some of the edge can still be removed so that the graph is still connected. So in such a case, we can remove as many edges as we want so that we keep only the relevant edges to make the graph connected. Then in that case, it must be a tree. Okay, so in this scenario, for this problem, so the blue edges form a spanning tree. And sometimes the edges in the graph would have weights. The weights could represent the cost of using the edges. For instance, we may be connecting the vertices in the graph together by some electrical wires. So these represent different buildings. And then these represent that if I want to connect these two buildings together by electric wires, then we will need 4 units of cost. Maybe the distance here is 4. The distance here is 7. The distance here could be 14. It could be like, and there may be a hill or some hard rock here, so that it makes it difficult to connect these two together by electrical wire. So suppose that we want to connect everything together so that electricity can be transmitted from any place to any place. So in somehow, we want to find all the edges that we need to connect them together, but then the total weight is minimized. Okay, so for this particular example, we have a scenario of finding a spanning tree such that the total cost is equal to 37. So we have 4, 8, 7, 9, and then 2, 4, and then 1, 2. So it adds up to 37. And then the minimum spanning tree problem is to find a minimum weight spanning tree. And notice that in the previous example, we have this scenario, it adds up to 37, but then it is indeed the minimum possible weight. But then it may not be the only solution. For instance, let's say if we do not use this edge, but we replace it by this edge. Now we will see that after the replacement, the graph is still connected, right? And then the total cost is still 37. So in such a case, we see that there could be more than one solution for a minimum spanning tree problem. Okay, indeed, the original problem is studied in 1926, where Borufka gives the first algorithm, and then it was indeed used to solve the electrical coverage of a certain country called Moravia. And then in 1956, Kruskal proposed an algorithm. We will study this together today. And then Yarnik and Prim, they independently invent the same algorithm, which is now known as Prim's algorithm. So we call this Prim's algorithm because it is first known more in public by as the invention of Prim, but indeed people find that Yarnik, because at that time the circulation of the academic documents is not that easy, so that even though there was a result earlier, much earlier in 1930, nobody knows about this result. So people knows this algorithm first as Prim's result, so it's nowadays called Prim's algorithm. So we will also talk about this Prim's algorithm today. So today we will talk about Kruskal, Prim, and also Borufka. Okay. And then there are more and more improvements recently, so that one can give an algorithm using E times log star V time. So this log star V is the iterated log function. It means that how many times do we need to take log in order to make a number less than or equal to 2. So this log star value usually is a number that is less than or equal to 5 for real life problem, but it is still not a constant. So although for most of the problem, it is less than the constant 5, but then we still do not call this order E time algorithm. And then Gable and the others, they further improve the algorithm to something like log star is already a small number, but then if you take log of this small number, it is even much smaller. So they have an algorithm like E times log of log star V. And then Chassel, in 1999, he gave an algorithm which is currently, I think, is the best still. So E times the inverse Ackermann function. So again, this inverse Ackermann function is a number less than or equal to 5 or even 4 in real life. But then it is still slowly growing, and then we don't call this a constant. Okay. Okay. So all these algorithms, all these Kruskal, Prim, and Borufka, they are based on the same observation. So which we call it the greedy choice lemma here. Now, before we move on, let us make an assumption. Okay, we assume that all the edge weights in the graph, they are all different. Okay, but you will see that, oh, well, maybe this edge and this edge, they are indeed the same too. Then what should we do? Okay, so if there are edge that has the same weights, then in that case, we will just arbitrarily say one is larger than the other. So you can think of this as 2.00001 and it is 2.0000. In that case, you will assume that this is longer and this is shorter. So when using this ordering, you can have any arbitrary ordering. It's just fine. Okay, in that case, we can make sure that all the edge weights are now with distinct value. Is that okay? So when all the edge weights have distinct value, then we can talk about this greedy choice lemma now. So here we define for each vertex V, EV to be the cheapest edge adjacent to it. So notice that all the edge weights are now distinct. So EV, the edge connecting to V with the smallest weight, is unique. Okay. So for instance, this is vertex A, and then A has two edges connecting to it. So 4 and 8. So we will call this edge EA. And for this vertex B, B is connected to 2, 7, and 6, and we will call this edge EB. And for C, C is connecting to 2, 4, 7, and 8, and we will call this edge EC. Is that okay? So suppose that C also connects to some other edge which has weight 2, but then these two and the other two are having different weights. So we will pick one of them as the unique edge weight with the smallest edge weight. Okay, now, so we will see that, okay, so this is important. So for each vertex V, the EV is unique, okay. And now there is a theorem. It says that the minimum spanning tree of the graph G must contain every EV. So in any solution of the minimum spanning tree, it must have this edge, it must have this edge, okay? Reason. Okay, the reason is actually very simple. So we can prove this by contradiction. So for instance, let's call this edge, so let's focus on the vertex V, and let's say EV is this edge UV. Is that okay? But suppose that this edge is not appearing inside the minimum spanning tree. So for instance, maybe V is connected to some other edge like VW, whatever. Then we claim that by adding the edge UV, the tree will have a cycle. And in fact, it will have a cycle containing V blah 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 up to U and then back to V. The reason is very simple. It is because without this edge, we have a spanning tree. And spanning tree means that for any node, we can connect using edges to the other nodes. So in that case, ignoring the red edge here, there must be a way for us to connect V using the edges in the spanning tree to U. So if you include the edge UV as well, then it will form a cycle. Is that okay? Now, interestingly, if you look at this, the blue edge VW is a tree edge, and the edge red edge UV is now not in the tree at this moment. But how about we do some changing? Let's not use the edge VW, but we replace it by the edge UV. So we will change something like this. Now, after the change, we are just doing what? We are just breaking the edge, but then we still connect this edge back. So we will see that everything in the graph is still connected. So if there is a vertex that connects from somewhere to U using a certain way without using the edge VW, then good. It still go along this way so that it is still connected. If it needs to use VW, then we will replace it by the edge starting from VU to whatever node that it wants to go. So in such a case, breaking the edge VW and replacing it by the edge UV will still keep the graph connected. But then the change here is we are replacing a longer edge with a shorter edge. We are replacing an edge with larger weight with an edge that has a smaller weight. So this gives us a spanning tree that has smaller weights than the minimum spanning tree. And this gives us a contradiction. Okay, so what does that mean? So it means that our first assumption that UV is not on the minimum spanning tree is wrong. And so we have proven the theorem. So every edge EV must appear in the minimum spanning tree. Okay, so this is the key idea. Okay, so it will be used in every algorithm that we talk about today. Okay, and then based on the edge that we now know, it must appear. So for instance, EA must appear in the minimum spanning tree. And let's say this edge EB and also the same as EC, they are all appearing in the minimum spanning tree. So what does that mean? It means that we can imagine that once we know that this edge is there, we can now connect the nodes here into a single node and connect the nodes here into a single node so that we just need to focus on finding the minimum spanning tree to connect the nodes in this new graph, G star. So G star is obtained from G by merging the nodes here and merging the nodes here, each one of them into a single node. Is that okay? So we get a graph G star, and then we will find the remaining edges that we need to connect the nodes in the G star together. Okay, and in that case, this is now the same problem as before. We are still finding inside a graph what is the minimum weight edges that we need to connect them together. So this is another minimum spanning tree problem. So we can solve this problem recursively. Okay, so this is the so-called optimal substructure property that we have seen in the dynamic program and also the greedy algorithm example. So here we are using greedy. The greedy choice is we pick this edge and we pick this edge. Okay, so we can prove the substructure property is correct by using contradiction. So it is left as an exercise for you, so you can now do so easily by yourself. So suppose that the green edges that we need to join them, yeah, is not the minimum possible, then there is something wrong. Or yeah, so think about this, okay? So once we now know this greedy choice property, so the greedy choice is for each vertex, the edge that has the minimum weight connecting to it is always in the spanning tree. Then we have the first algorithm called Kruskal's algorithm. So Kruskal's algorithm looks at the graph G globally and find the cheapest edge. Okay, once this edge is obtained, then we know that it must appear in the spanning tree. So we will select this edge and then we do the contraction, merging the two nodes of this edge together into a single node, obtain the new graph G star, and recursively solve the problem of minimum spanning tree. So it's like this. So we have this original graph. What we need to do here is that we look at the whole graph globally and find out which edge is having the smallest weight. So this is the smallest weight edge. So we merge them together. Now the blue part, originally there are two nodes here, but then the blue part here is now considered as a single node. So this blue node will now connect to this red node with two edges. Okay. So now after that, then what should we do? After that, we will solve the subproblem. This problem is consider this new graph and then select the minimum weight edge. So the next edge should either be this two or this two. But then one of them is smaller because we assume that all the edge weights are distinct. So let's pick the smaller one. I forget which one is smaller, but okay, so this one is smaller. Okay. So we are now picking this one. And so these two nodes are now merged into the same node. And then after that, we will pick this edge. This edge is now the smallest weight edge. And then we merge this blue nodes with this node together, and so all the three nodes here originally, they are now merged into the same node. Okay, so if we interpret this graph, we have how many nodes here? 1, 2, 3, 4, 5, 6. 6 nodes. Is that okay? So after each round, the number of nodes should decrease by 1. And then this blue node is connected to this blue node with 3 edges. So it's not a simple graph anymore. So there are 3 edges. Okay. And next, we pick this edge. This is 4. So 4 is the smallest. And next, we pick this edge. This is smallest. And then after that, what should we do? After that, let's take a look. The next edge that we should pick is this 6, because 6 is now the smallest edge in the whole graph. But then, when we pick this 6, we will not select this edge, because this edge is actually connecting the blue node to itself. So it is forming a self loop. So we don't want a self loop. We need a tree. So in that case, when we look at this node edge, then we will just take it away, ignore it. And then the next edge, maybe we are going to look at this 7 or this 7. If we look at this 7, then it is also forming a self loop because it is joining this blue thing. All of them are considered as the same node, right? It's joining from this node back to itself. So we will also ignore this one. And after that, we will select this 7. And then after that, we will select this 8. And then after that, this 8 will be seen, but then it is now dropped because it's joining to itself. And after that, we will select the 9 and done. So once we have included every node in the spanning tree, yeah, then we are done. So the edges that we have selected will be the solution of the minimum spanning tree problem. Okay, so easy, right? So how do we solve this problem using data structure to help us? So how do we find the cheapest edge? How do we perform contract? How do we detect whether an edge will form a self loop or not? Yeah, it is actually fairly easy. So first of all, we will see the edges in the graph globally. So what we are going to do here is we will first sort the edges according to the weights. And then from time to time, we are going to merge the nodes together, right? So we are going to merge these two nodes into the same thing, merge these two nodes after that into the same thing, and so on and so forth. So in that case, what we need to do here is we need to keep a union-fied data structure. So whenever we have merging of two endpoints from different components, so initially all the vertices are in different components, and then we are selecting an edge. We will first see whether these two vertices of the edge selected, the endpoints of the edge selected, they are from different components. If it is the case, then we will join the components by the union operation. And if they are in the same component, then we will of course we will also see that by finding the corresponding component, we see that they are in the same component. Then in that case, we are just seeing the edge and then dropping the edge. Okay. So the time complexity is simply E times log of E. This is the part for sorting the edges initially. And then the latter part is we will see each edge and then whether we will take it into the spanning tree or we will drop it. So in that case, there are E operations of union find. So each operation takes alpha E time. So in the end, E log E is dominating. So E log E can be expressed as E log V because you need to have at least V edges and then E will not be more than V squared. So this is like E log E is the same as E log V. So the whole algorithm runs in E log V time. So actually, the sorting of the edge is the bottleneck of the Kruskal's algorithm. So if we do not need to sort the edges initially, then we can actually run much faster in alpha E time. Okay. So far this is the Kruskal algorithm. Let me check if you are okay with this. Go directly to both U and okay, very good. Thanks, William. So let's see. So we are replacing the. So I think you are asking about what happens if we replace the edge, VW by the edge UV. Okay. So let's see. Okay. So let's see what happens. Okay. So if previously there is anything that needs to use these edges to connect to something else, so the only difference is when this edge is gone, what will happen? So when this edge is gone, so something is like, so first of all, if it needs to connect using the edge VW, initially, perhaps you have something that joins to V, connect to W, and then W joins to that other thing. Let's call X to V, V to W, W to Z, something like this. Then in that case, using the new replacement, X can go to V, travel along this dotted line, and then go to W, and then we still can go to Z. On the other hand, if previously the two things they are connecting to each other do not need to use this blue edge, then in that case, they are still connected without using this blue edge. Okay, so they are still connected as before. So in that case, we will see that whenever things are connected in the first case, they are all also connected in the second case. Okay? Okay, thanks. Okay. Okay, so this is the first algorithm. Easy, right? Yeah. Okay, so let's take a look at the second algorithm. Second algorithm is Prim's algorithm. So Prim's algorithm is not like global searching, it's a local searching. So Prim's algorithm starts with some U as the source vertex. And then because we are picking U as a source, so we will need to include the edge EU, the cheapest edge connecting to U. into the spanning tree. So this is what we are going to do. After that, we merge the vertices of the selected edge, so we get a smaller graph. And then in that case, let's rename that graph as, rename the vertex as U. So we are growing the vertex containing to the source vertex. So we will see the example, and then we will recursively solve the smaller problem. What does that mean? Okay, so let's see. Let's see this example. This is the original graph. We pick a particular node, let's call it U, specially as the source. So we will start growing, and then we are actually always growing the spanning tree by selecting the edge that connects to U. So how can we do so? So first of all, this is the smallest edge connecting to U, so we'll include it. So by including this, then we will do the same thing. We will merge the two nodes together into a single node. And then this is now the new node U that we have. Okay, we will keep this as the source node. Okay, and then after that, this is the source node, and it is connecting to outside by an edge of 8, an edge of 11, and edge of 8. And then we will select whichever is the smallest. I think this is the smallest one, right? So let's see. Oh no, this is smaller. Okay, so there are two 8s here. So let's say this 8 is smaller than this 8. Okay, so we will select this. So after the selection, then we will merge things together. So this is the now U that we have. So if this is the U, then we will look at all the edges connected to this U with the smallest weight. So this new U will connect to 8, 11, 2, 4, and 7, right? So in such a case, 2 is the smallest one, so we will include this 2. Okay, and now we grow the U, we will connect to 8, 11, 7, 6, 4, 7, right? So we will next include this edge 4. So we will have this one, and then after that, we should include this edge 2. And after that, we should include this edge 1, right? So at this moment, okay, after adding this edge 1, we will include this edge 7. And then after that, we will see that, oh, why do we include 7 but not 6? For the same reason that this edge 6 is connecting to two nodes that are already connected. So this 6 should not be considered. This is going to form a self loop. So we drop this edge 6. And then we include this 7, drop this edge 7, drop this edge 8, drop this, and then we will include this 9. So when everything is included, then we have a spanning tree, and this is the solution. Okay? Now, the good thing about this algorithm, so previously we will have a union find data structure. So in Prim's algorithm, in Kruskal's algorithm, we will have a union find data structure. But here we have something that is nicer, a little bit nicer, because everything is now going to be related to U. So we are expanding the source vertex U by including a new vertex after each step. So we will see that we can just determine whether, so a node will be included once. So once it is, so the first step includes this node into the source, make the source larger. The next step includes one more node and one more node, and so on and so forth. Actually, if a vertex is included, that means that it will be on the spanning tree forever. So instead of checking whether two nodes are joining to each other, they are already in the same component, then what we need to find out is whether the node of the endpoints, whether the endpoints of an edge, they are already both in the spanning tree or not. So we have a different way to check whether later there is an edge here. Yeah, this is some edge that is forming a self loop. So we have a different way to check it. So let's see how we can do so. Okay. So first of all, Prim's algorithm here, we use an easier approach. Let's say we use a binary heap to help us. This is not going to be the fastest one, but let's start with the easy one, binary heap. So the binary heap is doing what? The binary heap is keeping. So what is the best way that the source node can connect to a certain node? So this is what we are doing here. Initially, this is the source node, and then we don't see anything in the graph. So all the nodes here are not connected to U in any way. But then when we select U here as a source node, we will see the edges connecting to U like 4 and 8. So after that, we will know that this vertex can be connected to the source with an edge at most 4, and this vertex can be connected to a node to the source node with an edge at most 8. And after that, what we need to do here is that, okay, we will select the vertex that is connected to the source with the shortest weight. So we will add it by adding this node. So let's see if I have an example. Okay, I didn't have an example here. So, but perhaps, let's see if I can do something here on the graph. Okay. So perhaps initially, let me see if I annotate text. Okay. So what we are going to do here is, so initially, this is infinity. So let me see if I can make the graph that looks nicer. Okay. So initially, every vertex is not known by the source. Give me some time. Okay, so every vertex here has a value of infinity storing into it. This represents that the current way to include the minimum edge to include this into the current spanning tree is infinity. And then, but then for U initially, it is 0. Okay. Okay, so this is 0. At the beginning, it is 0. Okay. Now, because U is the source node, so what we are going to do here is we can now include, because of this U, we can now include the neighbor of U by looking at the edges connected to U, and then we will see that this, after seeing the edge here, we know that we can at least include this node into U into the spanning tree with distance of 4, and then we will include this one into the tree with distance of 8. Is that okay? But notice that this may not be the best way because we may have better way later. But at this moment, we know that we can do so. Now, this is one with the smallest weight, and then we will choose this edge, right? By picking this edge, then we will know that this is 4, so that we can now explore the edges connecting to this one, and this one. This is already done, included. This is not done, but then this is 4. By seeing that there is a way to include this one as 4, but then 4 is now in the source node, bigger source node here. So I know that we can have a different way to include this node with 11. But then we do not need to update this 8 because 8 is now better than 11. So we just keep it 8. But on the other hand, by seeing this node, we will see that this is the now source node, and the source node connect to this node with 8. So we can now update this as 8. So this is what we can do next. So far, yeah, okay, so far no problem, right? So after that, what should we do? Okay, after that, let's say this is an 8, this is an 8. We will use the minimum, the binary heap to tell us that, oh, this is the smallest one. Okay, and because this is the smallest one, then we will look at the edges connected to it so that we will now update this as 2. And we will now update this as 4. And then we will now update this as 7. Yeah, sorry that my drawing is a little bit messy here, but I hope you understand what I'm talking about. Oh, by the way, let me also do some coloring. Okay, so this node is done. So let's change the color to blue. Okay. Blue means that it is already on the spanning tree. Let's say this is also blue because it is now on the spanning tree. And this is now blue as well. This is now on the spanning tree. So far so good, right? And now, all the blue nodes we do not need to consider, but then we look at all the black one. So the black one, we will pick the one that has the minimum value because it has the minimum way to connect to the source node here. So this now 2 is now the smallest one, so we will include this 2 into the spanning tree. And by including this 2, what will happen is we can now look at the edge joined by 2, so that suddenly this is now no longer 8. Previously, this node is connected to the source with a distance of 8. But now, as the source now include this node here, there is a better way to connect this node. So we just need 7 to connect this one. Previously, this node is infinity, right? But then here, we are now making it better. So we can connect this node to the source with a distance of 6 only. So in that case, we will update it as 6. So this is the current spanning tree that we have. And then we will look at all the black nodes, find out which one has the smallest weight. So this is the smallest value, right? And then in that case, we will take this away. So using the binary heap extract mean, so we will find out this node and then include it into the spanning tree. And then because of this, because we are including this, we can look at all the edges connecting to it and then do some updating. So in that case, this one will be updated as 10. And then this one will now be updated as 2. And then we do not update the blue node. Okay, so it's blue already, so we do not update. And then after that, we look at all the black ones. So this is the smallest value. So when it has the smallest value, we select it by using the extract mean operation. When we have extract mean, then we look at all the edges that it is attaching to so that we may find update to some black nodes. So this node can now be updated as 1. So here it is a decrease key operation. So we decrease this to 1. Done with the updating, then we will look at all the black nodes again, select one which has the smallest value, this one, and then we change it to a blue one by including this into the spanning tree. Is that okay? And then there is no updating because all the nodes that it joins to are already in the spanning tree. So here we are not using the union find. We just check that it is already done, already done, already done, already done. So we do not need to do any updating anymore. And next we will choose this one. By choosing this one, then you will make it into the spanning tree. And then we will update this one. This is a neighbor of it. So we will update this. And then finally, we will have this one selected. So once all the nodes are now blue, then it means that they are somehow already in the spanning tree and then we can stop the algorithm. Is that okay? Yeah, I hope it looks good, right? So this is how Prim's algorithm is performed. And then, okay, so that's it. So you need to, so you can say it is, we are going to insert all the edges adjacent to V into H and then, oh, okay, this is another way. Binary heap, so here, it's not as efficient. So you can check it. So in this binary heap approach, let's read it together. So in each step, we find the cheapest edge that is already considered. So let's say the cheapest edge goes to a new endpoint V. We will include this vertex V into the spanning tree and then insert all the edges adjacent to V into the heap. So every time we are going to do insert and extract mean, and there are order E insertion extraction, so order E log E time. Okay, so this is the binary heap approach. But on the other hand, we can see that what we really need is we are going to have insert and decrease key. So in such a case, then we can use Fibonacci heap to help. So Fibonacci heap is efficient in the case that when there are many insertions, but there are only few extract mean. Okay, so in our example here, we are looking at extract mean of the what? Of the vertices that has the current minimum value. So we are actually having V extract mean only. So instead of having E insertion and E extract mean, then using a Fibonacci heap, we can make it faster. So somehow, yeah, this is what we can do. So we are going to insert the vertices initially into the heap, and then by updating the edges as we are showing in our example, there are many insertions. There could be order E insertions, but then and then also order E decrease key. Okay, but then there are only order V extract mean. So what we are doing here is initially all of them are inserted, all of the vertices are inserted with value infinity except U has value of 0. Then what we are going to do here is that whenever we include a new vertex, we will perform decrease key based on the edges of the new vertex. So when U is included, we perform decrease key, And when this one is inserted, we perform decrease key. So altogether, there are order E decrease key. But then every moment, every step, we just need to perform extract mean for a vertex. So we extract the vertex that has the minimum value. So there are only few extract mean operation. So altogether, if you check the time complexity of a Fibonacci heap, then with V insert extract mean and E decrease key, the total time is E plus V log V. So it is much better than E log E. Is that okay? So by using the Fibonacci heap, we can speed up the algorithm. Okay. So this is our example. Okay. Yeah. Initially, yeah, I think, yeah, this is exactly what we were doing before. Okay, so done. Okay, now let me double check if you are okay with the explanation so far. Okay, good, cool. Okay, and finally we have this Borufka. So Borufka is some kind of global algorithm again. Okay, so we will look at the whole graphs at the same time, but each edge that is connected, for each vertex, it will find out what is the cheapest edge that is connecting to it. But then what we do here is we perform the contraction at the same time simultaneously to obtain a smaller graph. And then after that, we find the minimum spanning tree of the smaller graph. So let's see the example. Okay, this is the initial graph. And then for each vertex, we find out what is the shortest edge connecting to it. So U will find this edge. This vertex will find this edge. This vertex will find this edge. This vertex will find this edge, and so on and so forth. And then after one step, we find the smallest edge connecting to each vertex, and then we will contract these connected components together. So this is the edge that we will select an edge. This edge is selected because this is the shortest edge connecting to this node to this one. We will select this because this is the shortest edge connecting this node to this one. We will select this edge because this edge because it is the shortest edge connecting this one to this one. So in the first iteration, we find out all the blue edges, and then the connected component of the blue edges will now shrink or merged into a single node. So after one step, originally there are many nodes, but then after one step, we have just one node, two node, and 3 nodes. Is that okay? And then what we do here is, after the next step, there are just 3 nodes, 1, 2, 3. And then for each node, we will find the shortest edge connecting to of this one to the other one. So for this blue one, the shortest edge is this 4. For this blue one, it is connecting to the outside by 8, 7, 6, 4, 14, and 10. So 4 is the smallest. And then for this node, this 8, 11, and 8, this 8 is the smallest. So what we are going to do here is we are going to make here. So when everything is now connected, then we end the algorithm. So this is the Borufka. So Borufka is nice. It is because we are making operations, we are making decisions. Actually, although we do a global way of merging the nodes together, but then in the first part, each node can independently select the cheapest edge that it connects. So this part can be done in parallel. So you can find the first node can find the cheapest edge, while the second node can find its cheapest edge, and so on and so forth independently. So they can do this at the same time. So Borufka is very good if we run it on a parallel machine. Okay, so that's it. So the correctness of Borufka is again based on the optimal substructure property. So let's see how it runs. Okay. So because each vertex V needs to find the shortest edge, so the total time for this part is order E time, because for each vertex we can visit its adjacency list and then see each edge and then retain the one that has the minimum value. So order E time, there's no sorting involved, so we don't need to do any sorting. And after that, after one step, we have selected the edges. So the graph contains selected edge and unselected edge. So we can use the connected component algorithm to find out what are the paths that are connected to each other, and then use linear time to contract each connected component part into a single vertex. So we will now get a smaller graph, so the number of vertices will be smaller. So because we now know that each vertex here contains at least 2 original vertices, so what does that mean? The number of vertices in the new graph must be dropped into at most half, okay? Although there can still be a lot of edges. So the edge may not change a lot, but the number of vertices will drop by half. So it takes order E time to find out the connected components and then make it into a new graph G star, okay? So this is what I have just mentioned. The number of vertices will drop by half at least. So it means that Borufka algorithm can only run in log V rounds, because after that you will just have one vertex left. So the total time for Borufka can be analyzed as just order E times log V, because there are log V rounds. Each time we may still have a lot of edges, so each time we have order E time. Order E times log V rounds is E log V. But then we can have some trade-off. Okay, so this is a very interesting way in theory that we can combine Borufka with the Prim's algorithm together so that we can have a better performance in some scenario. Okay, so first of all, what Borufka did was it will drop the number of vertices, but it will not drop the number of edges. So what we are going to do here is we are going not to run Borufka for a long time. We run Borufka for only log V rounds. The purpose of this is by running this in log V rounds only, the number of vertices is already filled. So after that, when the vertices are filled, we can switch back to the Prim's algorithm, so that this is the performance of Prim's algorithm. It depends on the number of vertices multiplied by log V. So when we run it by log V rounds, we don't spend a lot of time of using the original Borufka as we run it until the end. So the time of Baruch is bounded by E times log V, because we are not running it until the end. But after that, the number of vertices will drop. Drop into what? Drop into only having V over log V vertices. Yeah, because we run it each time, we drop it by half. Running log V rounds, we drop it into V over log V. But then this is now small. Even though if we multiply this with log V, it is just E plus V. So it is now fast for the remaining part by just running the Prim's algorithm. Okay. So in such a case, the total time is E log V. So the remaining part we can be fast. So E log V may not be better than Prim. It really depends on the size of V. But for some cases, for some scenario, when E is large but not that large, in that case E log V will be better. Okay, so this is the running of Baruch's algorithm. Okay, so that's the minimum spanning tree algorithm. If you are still okay, yeah, so let us, yes. Oh, very good. Thanks. So for all these problems, we will assume that all the edges are having distinct weight. So even though they look the same, let's say they are all 2, okay, but then this 2 is not the same as this 2. So we will never form a cycle. So each one vertex has a unique edge that is cheapest connecting to it. So we have a theorem that shows that the cheapest edge must be in the spanning tree, so they will not form a cycle. Okay. So imagine, let's have a very simple example. Let's have an example that is just having 3 vertices. They form a triangle. Each one of them is 1, having edge weight 1. But then the ones are different. Okay. So one of the one is larger than the other 2. So for each one, they will never select the largest one. So in that case, even though all of them are having the same weight, we will not form a cycle. Is that okay? Okay, so let me see. Okay, so let's try to finish another topic together today. Ah, there's so many pages. Okay, at least let us see if we can do so. If not, then we will leave some for the next week. Oh, by the way, I'm sorry that this Friday I am having an interview. So student, I'm interviewing somebody, not I'm being interviewed. Okay, so I won't be able to have a class, but I will make video recording so that you can check it. So it's going to be about exam 2 solution, and also yeah, or perhaps homework 5 solution. Okay, so let me really double check if there are any further questions, because we are now going to start something new. Okay, thank you very much. Thanks. Okay. Okay, now we have a different problem called single source shortest path. Okay, so we will first mention what is this algorithm about, and we will introduce a Dijkstra algorithm. And then this algorithm has a lot of similarity with Prim's algorithm. And so let's stop after this, and then we will leave the folklore algorithm for DAG and the Bellman fault for the next time. So today we will first talk about this part and finish until the Dijkstra algorithm. Okay. So what is the single source shortest path problem? Again, we have a graph G, and then this graph is a weighted graph. And then the edges in G has weights, and then the graph could be directed or undirected. It could be connected or disconnected. And the single source shortest path problem is we have a source S. We want to find out what is the shortest way that we can travel from S to each different vertex in the graph. So for instance, let's say this is the source S, and then you will see that, oh, this graph is something that you have seen just now, but we are not solving the minimum span tree. And what we want to find out here is that for each vertex, we want to find out if I want to travel from S to that vertex, what is the minimum length path that I need. So for instance, this vertex is 4. For this vertex, we can travel it from this one to this one to this one with length 12. And this one says 14. So how can I get 14 for this one? So 4, 8, 2. So we get 14. And then how about this vertex? So this vertex, we can travel it like from the bottom, 8, 1, 2, 10. So in that case, we get 21. So notice that it is not the same as we find a minimum spanning tree and then find out the distance to travel from one node to the other node on the minimum spanning tree. It's not. We can use whatever edge in the graph. So it's not the same as finding a minimum spanning tree first and then finding the distance. For each vertex, we want to find out what is the shortest way to go it. So sometimes we may be using these edges, sometimes we may be using this edge, and so on and so forth. Okay. So for this algorithm, we are going to have the operation called relax. So relax is something that we have actually just used in the minimum spanning tree algorithm. So relax is whenever we have something that we discovered. For instance, suppose that we know that, oh, we have now included V, and then we know that V is already connected to S using some shortest way. So in that case, we can look at the neighbors of V and then find that there is a certain way that we can connect to each of the neighbor of V after the distance from S to V is known. Is that okay? So for instance, suppose that I know that from S to V, you can use a path of length 4. Then it automatically implies that from V to this node, not from V to this node, from S to this node, we can have a distance at most 12. So we can write down 12 here to indicate that it is at most. Now similarly, previously when we know that S can be connected to this node by as a distance by 8, when you look at this node V here, suppose that we now know that V can be connected to S by a distance of 4. And so at this moment, we know that there is a way to connect from S and then to V and then to this node with length 15. So we now know that for this node, there is a choice of 15. But then it is not improving the previous way. So we are just ignoring the improvement that the potential improvement that we just see because it's not improving. So the idea of relax is the same as Dijkstra algorithm. So let me explain it. You will see similarity, extremely similar to the Prim's algorithm. So what we are going to do here is we start with the source S. Initially, we know nothing about the shortest distance from S to each node. So we will list it as infinity here initially. But after that, what we can see here is that S can now perform relax because the distance from S to S is now known to be 0. So in that case, we can relax by looking at all the edges connected to S one by one. After relaxing, we will see that this vertex, the distance can be improved from infinity to 4 because there is now a way of 4 getting from S to this node. And for this node, originally infinity, but then after the relax operation, then there is a way from S to this node with length 8. So we will now write it as 8. After the relaxing operation, what we are going to do here is we are now choosing among all the nodes, all the black nodes, which one has the smallest value. So this node has the smallest value. So we are now seeing that this node must now be connected to S in the best way. Yeah, because we assume that, so here for this problem, we assume that the edge weights are all positive. Is that okay? So currently it has the smallest value. So it means that all the other nodes will, whatever that we know, will now have a larger value than this one. So there's no way that we can go first to some other node, back to it with even a smaller value than the current node it has. Okay, so what we can claim, okay, by using contradiction, that to see that the one the node that has the smallest value. So here, among all the nodes with the smallest value, this is correctly set as the shortest distance. So what we are now doing next is we include this node because it is now known to be a correct value. And knowing this to be correct, then we can perform relax for seeing all the edges connecting to this node. So by relaxing, this is from infinity into 4 plus 8. So we now get it into 12. Relaxing, we can see that this can be 15, but originally it is 8 already. So we don't need to change this because 8 is already better. So we keep it as 8 and that's it. So this one, you don't update because it is already known. The shortest distance is known. So we do not update. So after that, we are going to look at all the nodes, the black nodes with the smallest value. So the next part is we are going to include this node 8. Knowing that this value is correct, this represents the shortest distance from S to this node. And then we perform relax. So relax, relax, relax. So after relaxing, this is now 15 and this is now 9. And we repeat the process. So here we have 3 nodes. Yeah, these are the remaining nodes that we are not known about its shortest distance, but we select the one with the smallest value. This is the node 9. And we now know that this node is set correctly with the value. And then we perform relax, relax, relax. Okay. So by performing relax here, it is still 15, no change. Performing relax, it now is updated as 11. And then after that, among 11, 12, 15, this is the smallest one. So it performs relax. So we will include 11, relax, 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 relax. And then we will update this one as 21. And after that, among all the nodes with this value, the black nodes here, we are choosing this one. Okay. Relax, 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 relax. So relax, 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 relax. But then we don't see any update. So in such a case, we will stop this process for this node and then find the next one. So the next one is 15, include 15. And then the next one is 21, include 21. And then the final one is 25, include 20. No, there is a change here, sorry. So for this 12, I should have relaxed here to change it to 19. Yeah, sorry, I missed that. So 19. And then there's also an update here, sorry. 12 and 2 updated as 14. Yeah. So sorry for missing this. But in any case, after that, this is the smallest value. So we will include this. And then this is the smallest value, include this. And finally, this is the smallest value, include this. So when everything is included, then we have this structure. And you can see that this process will always include one node each time and then attach it to a previous node that is already in the with the distance known. So in the end, we actually have a tree structure obtained. And this is called the Dijkstra shortest path tree. Okay. So the correctness of this algorithm, you can prove it by contradiction, or you can see that this is also an easy way to prove that it is correct. So it says that the cave vertex closest to the source will be selected as a cave step inside the while loop. So the first step, we will include the node that is closest to S. So we include this. And the second step, we will include the second closest node. And then the third step, we will include the third closest node, and so on and so forth. So by proving this using induction is easy, okay? Okay. And now the analysis, yeah, if once we see that it is really similar to the Prim's algorithm, we immediately can see that the whole process can be implemented using the Fibonacci heap. So each relax operation is just a decrease key operation. So we maintain a heap for all the vertices, and then the key inside the vertex is the shortest distance from S to it. Okay. So we are having relax operation, and then it corresponds to the decrease key, the order E relax operation. And then each time we will select the smallest vertex to be to be included. So they are exactly order V extract mean operation. So in summary, order V insert or extract mean, order V insertion at the beginning. So we insert all the nodes at the beginning with value infinity, except that the source S has value 0. And then each round we will perform an extract mean. And each round we will perform decrease key operation based on the new nodes that we select. So order E together, because each edge is only seen at 2 times. Okay, so altogether, using this and this, by using the Fibonacci heap, the performance, we will see that the total time is E plus V log V. Okay, so this is the case, for the shortest path problem. Okay, I think, that's enough for us to study today. So I'll leave so there are 2 special cases that we will study next time. The one is, what if the graph is directed and if it is a deck, okay? And then the second problem here is, what if we have some edge that has negative value? Okay, so this is not something that is common in the daily life process, because in the daily life, distances are usually positive, but then in some problem, we may need to have negative value as the edges. So we will talk about this next time. Okay, so that's all for today. Any questions? If not, then let's end the class today, and then see you next week. So I will prepare for the recording of the exam 2 solution for this Friday. Thank you very much. Yes.